Today we will see something interesting, which is called as conservative force. Okay. So before going into this, what's a conservative force and all, a force is a very important thing in physics, in our physical world also, because we all are sticking to Earth because of force, right? That's a gravitational force. Every minute there's a one continuous force acting on all of us. That's why we are all sticking to Earth. Correct? So the force is one of them is a quantity which every one of us is experiencing, and every object is experiencing everything. So it is a very important physical quantity, that force. And because of force, many other things can come up. For example, so I am on a wall, I'm jumping down. Okay, so have I done some work? Because I moved from one point to another point, right? That means some work is done. So what the reason the work is done? There's a force. Because I am not, someone is not picking up and dropping me like this. I'm jumping. The force, the gravitational force, which is causing me to do some work. Okay, so the force is, because of the force, some work can be done. Okay, and now I am there. Okay, so now for me to go up, can I just by myself, will it come just like that, or I have to do some work, right? Some work. So now I have to do something against the gravitational force and climb up again. So then now again, if I jump down, I can again go down, right? So now if you see this whole process, so there is initially I was having at a higher altitude, and when I jump, the gravitational force is got me down there. So that has done some work. Now I am now there. Now from here to go back, I have to do some force. I have to apply against the gravitational force, go up. Okay. So now, so this is what. So then what happened when there's, so now when I did again some force and I reached up. So now at that place, when I am on the top of the wall or something, now I don't do anything. I just move out of the wall. Correct? See, something like this. Okay. If I just remove the wall, I'm not going to do anything. If I remove the wall, then see, now what happened? Now there is a gravitational force acting. Am I right? Gravitational force acting. So, but is there any work done? No, because there is no displacement. Suppose if I suddenly remove this wall, so then what happens? Then you will fall down. Am I right? Then you will fall down and the gravity is there, and then you will fall down on the ground and lie like this. Correct? Okay. So now what happened? Now I can't say the no work is done. There was a force initially and there was a force acting now also. So, but this force has caused some displacement as. Okay, then I can say the work has been done. Okay, so the work done will be equal to, you remember, the force into distance, the displacement. Okay, that's the work done. So now, so initially, so now, so that means you have done nothing. You just remove the wall and some work is being done. Suppose I am not removing the wall. Okay, so the wall is there and you are standing on it. Okay. Now, since you are here, you are not doing any work, but you have the capacity to do some work. The moment I remove the wall, you will do some work. So now the capacity to do some work is called as your energy. Remember, this is all in 10th standard. The capacity to do work is your energy. Here in our case, this is the potential energy. Am I right? Yes, because you are at a certain altitude. This is all you have studied in your 10th standard, in your earlier class. Now let us come back. So I am going to do a small experiment. And what we mean by a conservative force. For example, you must have all done this. You must have played these games. So you have a glass floor. Let me say you have a glass floor. And you are dropping a marble. Glass marble. Okay, let me use another color. You are dropping a glass marble at a certain height. You are dropping it. What happened? The marble will come down, fall, hit, and then bounce back. Am I right? Am I right? The marble will come, hit the ground, and then bounce back. Let me draw it. So what am I going to do? It's a glass marble. Huh? The glass marble, it hit the ground and then it bounced back. Okay. So now where it will reach the same height or slightly lower? Slightly lower. Okay. So let us say slightly lower. It's going to reach here. Okay. Very small, very little bit. Okay. If a glass is very perfectly, why this reaches slightly lower? You know the idea?
Because most of the energy is transferred to the ground.
No, not like that. Okay, so now, let us put up an experiment. Okay, so we are having, what we did, we had a glass marble, we dropped it, it bounced back and reaches a certain height.
Because while going down, it had the gravitational force to push it downwards.
Okay.
But while coming up, the gravitational force is its gravitational force is against its.
Correct. Okay. So now, then if that is the case, so let me make this as a glass tub and fill it with water. The same gravitational force acting everywhere.
But the water is the gravitational force. The force of water is released.
Correct. Now will it reach back the same height?
No.
Where it will reach?
It will stay down.
It will bounce. It can bounce. It can still bounce. A heavy ball, I can say in a glass also, it can bounce back. But will it bounce back to same height or smaller height? Smaller height. Why? The force of gravity is same.
But there's a repulsive force.
What is the repulsive force? The friction.
Okay.
The friction by the water, the fluid. Here, when I don't have the water, there's a friction by the air. It causes, that's why the ball, the glass marble, the glass ball, what you're doing, that it will not bounce back to the same height. Suppose, let us now take up the experiment. So now I am going to remove this glass water also. I have removed this water. And in this chamber, what am I going to do? Okay, and this is my glass. I'm going to cover up my glass bottle with a small knob, okay, and pump out all the air from it. So basically, I'm going to create a vacuum. And then I'm going to drop this glass marble, glass bar. So now tell me where it will reach. Will it be reach more than the earlier one in the air?
No.
Why? Initially, when I dropped the air, okay, let us take up. When I dropped the air, it reached here. When I dropped in water, it reached here.
Okay, it should go back to the same place, right?
Yes. Okay. There is no friction. So in that case, what happened? The glass ball, after bouncing back, it reaches the same place and keep bouncing up and down. Okay. And if there is no friction and if there is no energy loss in this, okay, so what is this happening is, initially, when the ball, you're leaving the ball here, there's a gravitational force which is acting, correct? So the gravitational force will pull the ball down, it hits the ground, okay? It hits the ground with the same gravitational force because we are saying gravitational force is constant. So now, Newton's third law will act. An equal and opposite force will be applied on the glass ball. Okay, so the glass marble will again move up, remain there, and then come back. Okay, so what you can see in this whole process, I said this is at a certain altitude. So this is having some potential energy. Am I right? Because certain height is there. It has some potential energy. When you drop it, the potential energy is going down. It reaches to some minimum value. Then again the reaction force is given. So when you move down, you are going down in the potential energy. Now once it hits back,
Okay.
so the glass base, the glass bottom, the glass floor is giving an opposite reaction, the same force. So now the same forces applied on the ball, okay, or the glass marble, okay, and the marble starts moving up.
Okay.
So now initially the potential energy is going down, now the potential energy is increased. So what we saw first, so let us repeat the whole thing, whatever experiment we have done. First what we did, we had the air, we passed air, we let us pass air in it. Okay? So now, so then with the air what happened, you are dropping the ball, it hit the ground, and then it bounced back. Okay, this gave a force, it bounced back to the maybe some lower height. Correct? So now I am going to, instead of air, I am going to fill it with a water. Correct? So let me write it as a water now. Yeah. Water. So I am filling this chamber with the water. I am doing the same experiment again. Okay, maybe a different place. Here what happens? So when I drop the ball, okay, it hits back and bounces back to some lesser value. Correct? Earlier it was like this. Okay, this is the case for air. And this is the case for water. Now I am going to do it, suck off all the water and air and create a vacuum. And let me do the experiment. So then what happened? Here, why this was going down? Because of the friction. Correct? So now what am I going to do? I am going to drop the ball here and the ball will again come back to the same position. Am I right? Hit back. Okay. So now if you see here, so here's what is the one? Here you have the friction or viscosity. By water. Okay. And here you have air friction. Am I right? So here nothing is there. No friction, nothing. When you have no friction, nothing. So what happened? So initially what you have done, you have applied a force and the force has done some work in moving the glass ball toward this distance S. And now the floor is giving a force and the ball has moved again the same one. So now can you tell me the magnitude of the work? What is I am saying? Magnitude of the work. Okay. So here what is the work done? Tell me. So here the work done will be in this direction. Suppose if this is the force, downward force acting is F, and if this distance is S, so the force will be equal to F dot S, F into S. Okay. So similarly, can you tell me about this path? Same Fs. Am I right? The work done is also again here equal to F dot S. Only thing is here the work is done on the ball. Here the work is done by the ball. Correct? The ball is doing the work. But they both are same. Okay. So the work done. So then it's interesting. So what happened? The work done. Okay. So will it be same for these cases? No. Right? Because the displacement is different. Correct. So here if you see, the work done is not depending upon the path. Whether it move from up to down or down to up. The work done is going to be same. That is not the case for air, in the case of air, in the case of water. So this force, when the work done, the force which does some work, and the work, when the work do not depend upon the, the path of it. Okay, so, and that type of force is called as your conservative force. Okay, these are not conservative force. This force is a conservative force because the work done is not depending upon the path of the motion. Okay, so what it says is if the work work done by or against. Okay, if the work done by or against a force is independent of the actual path. Okay, it doesn't matter about the path. Then the force is said to be a conservative force. Okay, so this is what called as a conservative force. Okay, it doesn't matter. So what happens? So if you want to, so what it says is, if you wanted to raise the potential energy of a certain body, you have to lift up. Am I right? So you are going to lift up. So if I give you the height of it, so you can lift up almost wherever all the height you give, that is going to be that will be always having a same amount of work has to be done. And if you drop also, the same amount of work can be done by the body. Okay, so they everywhere, so it will be independent of the path. Wherever you do, the same amount of work will be done by the particle or against the particle on the body. Okay, so this type of force is called as your conservative force. You got it? Clear? So now, fine. So this is what you call as a conservative force. So then I told you. So basically, whatever the force is, from the force, what the force is doing is either decreasing the potential energy or increasing the potential energy. Okay. So then we can do something. So that means the potential energy. Okay, so that means what? The potential energy is the capacity to do the work. So it will be equal to the capacity to do the work. Okay, so the work done when I leave the ball will be F dot S. Okay, and when I want to raise it back, the work done will be F dot S. Okay, so then I can write your potential energy as, remember, force is a vector. Am I right? What we have, force is a vector. Displacement is a vector.
Yes.
Work done?
Work done is not a vector.
Scalar, correct? So,
it takes the
dot product.
Okay.
Correct? The dot product. So, that is what equal to F vector, magnitude of vector into magnitude of S vector into cos theta. Remember, theta is the angle between F and S. Suppose if F and S have the same direction or opposite direction, so what it will be? Theta either will be 0 or pi, 180. So cos 0 equal to what?
Cos equal to
1. Cos 180 equal to?
0.
Minus 1.
Minus 1.
So the sign will be either can be plus or minus. Okay. So now, so this is the work done. So now we can say from here, so when the capacity to do the work, the magnitude of this work will be equal to the potential energy. If the no work is done, if I hold the ball, then what the ball is going to have a potential energy. Am I right? There's no work done, and that potential energy will be numerically equal to the work done, the capacity to do the work, right? So then your potential energy F will be equal to F dot S. Am I right? Of course, this is also energy is also a scalar. Then, and normally they use sign negative. Okay, why this sign negative is important? Potential energy, why the use sign is negative is, if you want to increase the potential, okay, so what you have to do means you have to raise the potential. Work has to be done, raise it. Okay, so the potential what happens, so it is will be opposite. To increase the potential, you have to do work on it, on the body.
Okay, so it will be opposite to the work done.
Not opposite to work done. The typically the sign is attractive when is attractive potential. For any attractive potential, so it's attracted, right? If you want to move to a higher potential, what you do is you have to apply some force and you have to, the work has to be done on the body. When the work is done on the body, then you call that potential energy as your negative potential energy. If the potential is giving energy, then you will have a positive one. Okay, it's a repulsive one. So this is what I'm saying. So this is what your attractive potential. That's why you get a minus F dot S. Okay. Okay. So okay. Let me see what else you have. Okay. They have done. Okay. What anyway you have done this infinitesimal. So now let us not move out of this picture. And let us see. So now, suppose if there is a force, so now we know about infinitesimals, right? Smaller decimals. So then what happens? So if there is an infinitesimal, a force has caused an infinitesimal change in the position. That's what a force F has caused an infinitesimal change in the position. Let me call this dx. Okay, then the work done will be equal to what? Then work done is the infinitesimal work done. Am I right? That will be what? dw will be equal to F dot dx. Okay, and this will be equal to minus du. The infinitesimal change in the potential. You got it? So, and this is what they've written in your book. Fine. Yeah. Okay. And one of why important thing with the conservative force is when the conservative force, the mechanical energy. Do you know what is mechanical energy? It is sum of the kinetic and the potential energy. Okay, this is a potential energy when I lift it. When I leave it, it's moving with a velocity. When they have a velocity, so it has what? Velocity means kinetic energy. Correct? What about the conservative force? This mechanical energy, that is sum of potential and the kinetic energy, will be always conserved. This will be conserved. Okay. Now you can say what do you mean by conservation? Of course, we have conservation of energy. Energy can either be created nor be destroyed. Correct. So what it says is only the mechanical energy will be conserved. That means the sum of the kinetic and the potential energy will be conserved. Okay. They're only for the conservative force. Now it doesn't mean that matter that when you drop the ball in a water, the energy is not conserved. There, the mechanical energy is not conserved. But energy will be released in some other form. That we will see later on. Okay, when what happens with non-conservative energy, what happens? Okay, the conservative energy, so only thing we know is conservative energy, the total mechanical energy will be conserved. That means the sum of the potential energy and the kinetic energy will be always same. Okay, will not remain, will not change. What they written in a book is the work done by or against the conservative forces. Okay, now you understand what the meaning of conservative forces, right? So it's an important line. The line is interesting. That gives a concept of potential. The work done by or against the conservative forces reflects an equal amount of change in the potential energy. Correct? You can see what happened earlier when the conservative force bring it down, that much of potential energy is being reduced. When you lift up, the same amount of potential energy is being increased. Okay, so that's what the concept of potential energy comes. It comes when you mainly when you deal with the conservative energy. Conservative energy will always give the equal amount of potential energy will be if the force is same, equal amount of energy potential energy will be potential energy will be changed. Okay, it will be always equal. The corresponding work done is used in changing the position. Correct? The work done. Even you drop the ball, there's a change in the position. Or you lift the ball, there's a change in the position. So the corresponding work done is used in changing the position or in achieving the new position in the gravitational field. Okay, in the gravitational field. Hence, potential energy is often referred to as the energy possessed on account of position. You understood? That's what they mentioned in the line. Okay, fine. So that's all we have to do it. Okay. Okay, yeah, fine. So then we discussed that, right? Where is the du? Correct. So now I ask you. So basically, what happened? It's a small dx. When I move from a small dx, infinitesimal displacement. So this is the infinitesimal change in the potential energy. So if you want to write what is the total change in the potential energy, what will you do? So I'm asking, so therefore what happened? Du is equal to minus f dot dx. Am I right? So I'm asking, so now this is for an infinitesimal change. So that means what? You are dropping a ball from one height to another height, another x. So this is a small distance I have done it, dx. Okay, and the energy gain by moving from here to here, that is your du, energy change in energy, I would say energy gain. Okay, so du, and that du will be equal to f dot dx. Okay, so now I ask, what is the total change in the energy? That means what? U. Am I right? Am I right? Is that you remember or not? Integrate it. Okay, there's a total change in energy. Okay, so you have to revise back those chapters, and you will follow it. Okay, U equal to minus f dx. Okay, and where minus f is a conservative force. Okay, this one we will discuss in chapter 5. Yeah. If friction or air resistance is present, we discuss that. Additional work is necessary against the frictional force, and this work is strictly, okay, and this work is of course strictly path dependent, whichever path you take, okay, whether moving downwards or upwards. So this force will be different, and so such forces are called non-conservative forces. Okay, when the force, the work done depends upon the path. You got it? So because what happened earlier in a water, what we did, how it comes up is simple. So you are having the water, am I right? Okay, so you are dropping a ball from here. You are dropping a ball from here. This amount of work is being done, right? Some work is being done by the ball. Now, if you want to raise the ball, the work done by the ball will not be equal to the one done in the vacuum, because it has to work against the water, against the friction, viscosity of the water. Viscosity, the friction of water called viscosity. Okay, viscosity of the water. Now, if you want to, now the ball is down. Okay, now you want to raise up to the same potential. With the same amount of work has to be done, because of course the force has to this plus you have to go against the friction, right? Here in this case, work done will be very less compared to vacuum, because the friction is going to give an opposite force. So okay, so which means the energy, some of the energy is lost. Okay, so this means the effective force here will be less because of the friction and the gravity. And here also, the effective force you have to give me much more, because you have to go, yes, against the gravity is against the friction. So now what happened? Are the work done is same in both the cases? Okay, because you have to give more force, you have to give, then it moves up. Okay, so that's what. So in this case, this force will not be a, it's called as a non-conservative force. Okay. Fine. Then this is important. The other one is a work done by a variable force. Yeah. This is an important one. Okay. If you remember, in earlier classes, you have done it. So, the work done, W equal to F dot ds, right? Actually, this. Okay, if you don't like ds, let me put dx. Doesn't matter. It's basically the displacement. Okay, whatever symbol you use doesn't matter. This equation is not completely correct, or you will not call dx. I should call it x. Because when you dx, it becomes w, right? So, what happened? Okay, let me write it as, or we want it as x? Okay, let me write it as x. Okay, so what it says is, the work done in moving an object from one position to another position, maybe here or upwards or horizontal, whatever. So if this is the force applied, and we applied on it or by the gravity or whatever, if this displacement is s, Okay. Then the work done is equal to W equal to F dot, sorry,
X.
X. Then the work done equal to F dot X.
Huh.
This is only true if your force is constant. Correct? Suppose you are dropping something from the top of a tower or maybe a top of a mountain. Somewhere else you are rolling down. So there the gravity is not 9.8. As you go above, over a certain distance, we can assume the gravity to be a constant 9.8. So there the gravitational force will differ. Am I right? There, this is not the case. So what the correct formula for the work done is not the case. The correct formula for the work done is, what we know is, take it for infinitesimal small distance. So what I should do is, I should take an infinitesimal. So let me call it dx. Okay. And over this infinitesimal region, I can assume the force is a constant. Am I right? So over this infinitesimal portion, I can assume the force is a constant. So in that case, I can case that the infinitesimal work done. Correct? There's a work done in moving an infinitesimal. So the infinitesimal work done, I'll call it as dw will be equal to F dot dx. So this is the correct formula. Okay. And this is not always the correct formula. This will correct only when the force is a constant. Okay, so this is the correct formula. Therefore, the work done should be always written as integration, the moving from the particle, let us say this is x1, x2 is the position. So then this moving from x2,
X1 to X2.
okay, x1 to x2. x1 to x2 will be equal to F dot dx. And F can be a function of x. F may differ over the different region. Okay, so this is the correct formula for. So what happened? Only what happened when your F is a constant. You remember in the integration we did. If it is a constant, you can take out of the integration. Okay, if F is constant, you remember that? Do you remember? Then the constant we can take out of the integration. So what we'll have is, if F is constant, then your W will be equal to F times integration of dx. Okay, there's a dot symbol. I'm leaving it up. Let us take, for example, they both are of same direction. So in that case, cos theta, that will make it to be 1 or minus 1, doesn't matter. Okay, so minus 1 says is done against the gravity or by the, is it done by the force or against the force? Okay, so F dot dx. So, and this case, if this dx is will be equal to what? Tell us x1 to x2. So that equal to F into x2 minus x. Am I right? So this will be what? So dx is what? Integration of dx, you know what is that? X. Okay. So if you have x1 to x2, so this will be a limit. We have x1 to x2. I think we all did this. Am I right? So this will be x2 minus x1. So this will be what? F into x2 minus x1, and that is this distance. Correct? And if you call this distance as s, so this is going to become fs. Got it? So this is what your the correct formula for the work done. Okay, and I think they have written something in your book. Let me read it. Okay, yeah, they have given some one figure. Okay, the same thing what I explained here, they explained with the graph. Okay, so you can do that. For our day-to-day life, see what happened, the gravity we are taking would be almost constant. We are not going to jump from the Himalayas to Mount Everest on the sea level. Okay, so in those cases, we can always consider gravity to be constant. Okay, won't change much. Okay, so this is one. Yeah. Okay, yeah, this is also interesting. Yeah, that we have to do it in a different way. When you plot this in the graph, then it looks interesting. So let us do it in the graph. So for example, if this is the force, I am plotting, see the force, I am saying the force is going to have a change as it moves down. Am I right? So if I have the force along this axis and the x along this axis, so as x moving out, the force is not going to be same. If the force is same over the distance, so then what will be the line will look like? For all x, the force is going to be same. Am I right? That will be what? It will be a constant line. Parallel to the x-axis. Correct? Suppose the force is not constant. Force is changing with respect to x. So let me say arbitrarily. So then I am saying that there is something is happening, some very alien sitting and changing of the gravity at different distances. So then what happens? Your force will go on something like this. Okay, somewhere else the force is less, somewhere else high, and somewhere is going on there. Okay, in this case, if you want to work done, if you want to calculate the work done under this type of force, of course you can't use this relation. You have to use only this relation. Okay, so let me say for in that case, if I want to find out the work done, maybe from x1 to x2. Yes, you have to take an infinitesimal first, right? So you have to take an infinitesimal area first. Okay, so this is what, and this is your dx. Okay, so you have dx. So now, so this infinitesimal, what the whole assumption? During this infinitesimal, your force is a constant. That means what? It is basically a rectangle. Am I right? So what is the height of this rectangle? Say something like this one. For suppose if it is f1, the height will be what? f1. What is the width of the rectangle? What is that width? It's infinitesimal, na? What will be height? Tell me what it is. What is that? What is that you written? dx, na? Dx. So what is the area of this rectangle?
F1 into dx.
F1 into dx. What is that?
Work done.
That is the work done. Am I right? So basically what happened? The area under the curve. Area is a work done. Okay, so if I find out the area, the whole area, so that means what? That's the work done in moving the body or whatever is happening as I move position, when the position is changed from x1 to x2. Okay, and that work done will be what? Will be equal to, you remember in the integration we are doing, the definite integral will come as an area under the curve. Correct? So x1 to x2 f dot dx.
That can be f1 dot.
Yeah, this is nothing but the area under the curve. Okay, so that's what they have mentioned here. Okay, they are given, where is the force linear? Okay, in this case, area trapezium will give total number of work done. Yeah, that's okay, there's nothing. So in this case, they are given another one example where the force is a linear force. Means the force is not a constant force, but it's linear. The linear means what? So you have the x here. Okay, that's nothing. So you have the x here. So if the force is linear, okay, and then the work done in moving this object from x1 to x2 will be what? Nothing but the area under the curve. Correct? So what will be the area under the curve?
One rectangle and a triangle.
Yeah, or simply a trapezium. Area of the trapezium is the work done. Okay, so this is what your direct application of your integration. So when you find out the area under the curve, here the area under the curve will be the work done. Okay, so you plot your force and the displacement, and with respect to distance, wherever the force is distance, and when you take the area under the curve, so within it to x1, x2, that gives you the work done, and that will be the amount equal to your potential energy or whatever the energy also. If the conservative forces, then that energy will be converted to kinetic energy, or potential, we will see it later on. Okay? Fine. So this says, so this is, with this one I explained, now you understood clearly what is meant by conservative force and what is the non-conservative force. Okay, and what exactly the work done, potential energy, what do we mean by potential energy, okay, and what do you mean by how this work has been done by all those things we can see. Okay, so ideally you should use a vector notation, okay, that you can see it also. Suppose for example it doesn't matter, suppose see you remember that you have a cart, am I right? Suppose there's a cart, okay, and you are pulling it with a rope, the force is applied here, but the cart will fly up and come to you, no, it will move here, am I right? So the work done is equal to what? So basically in this case your displacement, the force is in this direction and x is in this direction, so you have an angle theta, okay, so that means what? Basically resolve the force along this direction. What is the force along this direction? If you remember, resolving vector, if you have a vector, say something like vector x, so and if with angle theta, so what is the
X cos theta.
correct x cos theta? So similarly, the force is this direction. Along this angle will be what? F cos theta. This is the magnitude. Okay. So now you got the force along this x. They both are in the same direction. Okay. So then your work done will be equal to the force along the x, causing the change in x. Okay. So F cos theta into x will be equal to Fx cos theta. This is what we normally write it as a dot product. Am I right? For a constant force. Am I right? So, fine. This is what I have. And then next one is interesting. Okay. Now with that I will stop. The work energy theorem. Okay. This work energy theorem is basically comes from for a conservative force. Okay. And that's what I actually mentioned also earlier, because the mechanical energy will be conserved always. So that's what you will see. If there is a decrease in the potential energy, a body is falling down. There's a decrease, right? Potential decrease energy due to a conservative force. So all the thing is what says the conservative. You have to neglect the air friction. So maybe in a vacuum, you can neglect the air friction if the object is heavy, like a very heavy iron ball. It's moving down. Okay. Due to a conservative force, it is entirely converted into kinetic energy. Am I right? From the potential when it falls down, it gets converted back into, because initially it was at rest. Correct? So does it have any kinetic energy? No, zero. But there's potential energy. Now you are leaving it. It's coming down. At a certain height, of course, will it have potential energy? Yeah, because height is there. But that is smaller than the earlier one. But of course, it has added some velocity. Correct? So because of the velocity, initially there was no kinetic energy. Now it's having kinetic energy. What it says is that change in the potential energy will be equal to the kinetic energy at that point. You got it? So what it says is, so initially it is the potential energy, and the kinetic energy is 0, and here it has a less potential energy, add some kinetic energy, so this sum will be equal to the initial one. And similarly, when it reaches the ground, it's not going to break the ground and go further, it's going to stop there. At that point, it is having only the kinetic energy. So let us call that as 0. So then the whole potential energy is being converted into kinetic energy. This you must have done in your earlier class also, right? So this is what you call as a work energy theorem. If there is a decrease in the potential energy due to a conservative force, it is entirely converted into kinetic energy. Work done by the force then appears as kinetic energy. Correct? Vice versa. If an object is moving against a conservative force, its kinetic energy is decreases, because as you throw the ball up, the velocity is going to reduce, right? So there whatever it's going to convert back into the potential energy. That's what I'm saying. The whole thing, okay, you can take a ball, throw the ball up in the air, okay, and the same force, you throw the ball up in the water, it is going to be different. I mean, in the water it's very hard because the viscosity is very high. In the air water, you can even neglect to extend the air viscosity. Okay, so everything is valid only in the case of conservative force. Okay, the non-conservative force, it is not the same. Okay, it won't be the same. Yeah. Okay. So, if an object is moving against the conservative force, its kinetic energy decreases by an amount equal to the work done against the force. Okay, the same thing. Okay, this principle is called work energy theorem for conservative forces. Okay, basically this is what. Okay, and now let me do the one two cases. How this we can actually we can show it nicely from your equation of motion. Okay, let us see. Consider an object of mass m moving. Now here onwards we will consider only about the conservative force. Let us take the force is conservative, so there is no air friction, there is no viscosity, nothing. Okay, so in that case, consider an object of mass m moving with the velocity u. Okay, what they given? Let me start it. There is an object of mass m moving with the velocity u. Okay, velocity u. Okay, experiencing a constant opposing force. That means something like that you are throwing the ball up in a vacuum. Yeah, opposing the force. Let the opposing force be F. Okay, which slows it down to V. So this is the initial velocity. This force is going to slow down this velocity u to V. Okay. During a displacement S. But it has moved, right? So during let the displacement be S. So what it says is there is a body of mass m. Initially you are throwing up with a velocity u. Okay, now the force is acting against the body. Okay, so then what happens? So the force is going to slow down the velocity. Okay, so the velocity will reduce from u to v. Okay, and while traveling a distance of s. So if you remember the equations of motion, you have done the equations of motion, right? Do you remember that the initial here what happened? Our initial velocity is u, and the final velocity is v. Am I right? So what we say? Let us draw it pictorially. So this is the initial velocity, that is u, and the final velocity, that is v. Of course, v magnitude of v is smaller than magnitude of u. Am I right? Am I right? Correct. So now this distance it has moved is s, and the force which is acting against, that's a force F. Okay, so this is the picture we are having. Yeah, mass of the body is, so let us call the mass of the body is m. M is the mass of the body. Okay, so now if you remember, we have done the equations of motion. You know the initial velocity, you know the final velocity, you know the force acting, you know the displacement, then you can write the equation of motion. Do you remember the equation of motion? What is the equation of motion? One equation of motion is v square minus u square equal to 2as. Am I right? Where a is the acceleration. Correct? So now tell me. Yeah, correct. So now, well, so here the acceleration will be positive or negative? Acceleration will increase or decrease? Decrease. So it has to be negative. Okay. Or otherwise, what you can take? So minus 2a. U square minus v square. Yes. So u square minus v square will be 2as. So now let me do some jugglery. So you know the equation, Newton's laws of motion, right? So if you Newton's laws of motion, what it says, force is equal to mass into acceleration. So acceleration I can write it as F by m. Okay, so let me do it here. So this is going to be 2 into force mass into s. Okay, and then what am I going to do? Yeah, so let me divide by multiply by 2 m by 2 on both sides. So let me take the m here and 2 here. So what we are going to have, we are going to have m by 2 into u square minus v square equal to fs. Correct? Or I can call this as half m u square minus half m v square will be equal to f into s. Okay? And do you remember this is what you are changing the potential energy. Am I right? F dot is nothing but a work done. The work done is basically is a change in the potential energy. Am I right? So this will be nothing but your delta. What they given the symbol is delta U or just U. Okay, fine. That's right. You can have a. Let me write it down as. Okay, let me do U only. Okay. So the change in the kinetic energy. Let me write it as delta U. That is better. Okay. So what it says is the change in the kinetic energy is equal to the change in the potential energy. Am I right? So that means what? So when any change in the kinetic energy, the same way you can say it's a change in the potential energy will be equal to the change in the kinetic energy. Correct? Clear now? So this is what you call as your your work energy theorem conservation, because this is the total. So what it says is, so if I take the okay, actually I should put here minus here. So this should be actually against the one. We are doing against the gravitational force. Okay. So am I right? I mean the force. So now let me call this is a change in the kinetic energy. Am I right? So I'll call it a delta kinetic energy. So this is the minus delta potential energy. So therefore, delta kinetic energy plus delta potential energy is equal to 0. That means what? It is not going to change at all. The sum of the kinetic and the potential energy is going to be constant. This total sum is called as your mechanical energy. So the mechanical energy is going to be conserved only if the force is a conservative force, not a constant, conservative force. In a non-conservative force, this is not going to happen. Remember, not just constant, it's a conservative force. Okay, so you got why it's a conservative. It's not, otherwise it won't happen. That you can do it in your see, for example, okay, that we can do it in the case 2 they are given. I can just read that. See what happens. So for example, so let us consider the case of non-conservative force. So in a conservative force, this is going to be constant. So then what happens? So in a non-conservative force, so there is a, suppose the same thing you are doing it up. Okay. How will I go about it? Okay, let me read what I have written.
You can say like, because in conservative force, the initial and final height of the object will be the same. So the potential energy will also be the same.
Correct, of course.
But in non-conservation force, the potential energy will be lesser.
Lesser, because your sum of the work has to be done against your air friction. Okay, and that where that energy goes off is basically as a heat. Okay, the ball will actually get hotter. Okay, though of course you don't find it out, you don't feel it out, it gets slightly hotter. That's what the reason your meteorites and all they burn. The friction is so high, the stones, means even the rockets when they fall, they burn off. Because of the air friction, some of the work is done in heating up the body and the body burns. Okay, so in that those forces are non-conservative force. Okay, there your mechanical energy is not conserved. Some of the energy used up in heating. So you don't find any conservation of energy. That means mechanical energy will not be conserved because some energy is lost. Okay, so lost in different form. That's what. See, accelerating conservative force along with the retarding non-conservative force. That's what your accelerating conservative force means, is exactly. You are having a vacuum and you are dropping a ball. That is a conservative force. Now I am filling the chamber with the air. Now air is going to give a friction that's going to create a non-conservative force. The friction is a non-conservative force. Initially gravity is a conservative force. But the friction, the moment you added a friction, it's going to be non-conservative force. What it says is, an object dropped from the same point at a height h falls down through the air. While coming down, its potential energy decreases. Correct? Equal amount of work is done in this case also. The work is done the same amount. Okay, but the decrease in potential energy is not going to completely transform into the kinetic energy. The reason is what? Sum of the energy
Capacity to heat.
The heat. Okay, so even though you drop, say for example, from a certain height, you drop a ball at a certain height, you will find out a velocity. That velocity will be different or less when you have air in it. And that velocity is going to be much less when you have water in it. Okay, because the velocity is going to be slow there. Okay, or so when it is a vacuum, that velocity is going to be different, high. Okay, because it's a conservative. No, vacuum velocity also increases. Na? See, when you drop the ball, the potential is going to convert it. Okay, at a certain height. Let me draw another figure. So what I'm saying is, you are dropping a ball. Okay, over a distance. At a distance s, it may have a certain velocity, say something v. Now the v depends. So if it is a conservative force, initially what happened? You had only potential energy, right? So let us call the mass as m. So mgh. And now here the velocity is 0. So here you have velocity. Okay. So now, so this height. So suppose if this is the ground. So if this height is s. So here the potential energy is what? mgh minus s. Correct? Plus it has a kinetic energy also. Half mv square. Correct? So now this sum will be equal to this. Velocity increase. Suppose now over as it moving off, if the ball heats up because of the friction, that means there is some more energy is also there. Okay, some frictional energy, heat energy, frictional heat energy. Okay, now what it says, your conservation of energy has to be constant, total energy has to be constant. So it means this energy and this energy has to be equal. Of course, the velocity has to be, if this energy is not there, then the velocity will be slightly higher, then only it can be equal to this. When you have this one, some of the velocity is taken away by your, so the friction takes, not lost, some of the work done is done in heating up the body, so that reduces your kinetic energy. Clear? You got it? So that's what. So in moving the body from here to here, the amount of work done is same. Same amount of work done. In a conservative force, the entire work done will be converted into kinetic energy. Here, it is not. In a non-conservative force, that is not the true, because some of the energy is lost as a heat due to the frictional force. Okay, that's what they have mentioned here. While coming down, its potential energy decreases. Equal amount of work is done in this case also. Okay. However, this time the work is not entirely converted into the kinetic energy, but some part of it is used in overcoming the air resistance. This part of energy appears in some other forms, such as heat, sound, etc. Light, whatever you call. Okay, in a meter it burns up and gives light, heat, mostly heat. Okay, so in this case, the work energy theorem can be mathematically be written as, so in this case, the work energy theorem what? So earlier case, work energy theorem means mechanical energy is always conserved. That is, kinetic and potential energy will be always conserved. When it is a non-conservative force, what it says is, the work energy theorem says is, the change in the potential energy, that is what? Yeah, I have written here. The change in the potential energy will be, they have written the same symbol. Change in the kinetic energy plus work done the air resistance. Okay, so this is going to have the heat. The work done against the air resistance. Okay, so this is what. So decrease in the gravitational potential energy will be, this is what. The decrease in the gravitational potential is equal to the increase in the kinetic energy plus work done against the non-conservative forces. You got it? So magnitude of the air resistance, and this is important. Okay. So when you are dealing, when you have a non-conservative force on this acting, okay, you can't actually, if you remember the work done, what we wrote is work done will be equal to F dot ds. Am I right? So we took the force has to be a constant we can take out. When you have a non-conservative forces, you can't do that. Why? the air friction is going to depend upon the velocity.
Ah.
If you move higher velocity, higher the friction you're going to have.
Friction will be-
Okay.
Ah.
So then what happened? When you drop the ball,
Ah.
initially the velocity is 0.
Ah.
Now the velocity is going to increase. Am I right? So the air friction is going to increase.
Ah.
So in
Friction
that,
will decrease.
no,
Because
when it,
velocity will increase. Huh?
correct, of course, when the frictional force will be more, na?
Ah.
Why meteorite burns? When a stone enter into atmosphere, it burns off because it's at a high velocity. By sitting, it won't burn anything, right? If I'm standing there, air friction doesn't any effect on me? Of course not. I have to move. The faster I move, the faster the air friction. The same thing, like if you're not able to see it in the air, think about in water.
Okay.
You are in a water. Okay, that's what water will be easier to understand. Water, you can walk slow inside the water, in the swimming pool. If you're in the swimming pool, if you're walking, you can do still with the pressure. Can you run inside? Because there the velocity is going to be higher. Okay. So same way. So what happens when you drop the ball in the air, initially velocity is 0, no friction. Now as the velocity increases, the frictional, the non-conservative forces is going to increase, change. Okay, in that case, this force cannot be taken out as a constant. The net force. The net force, na? Because one is the gravitational force minus the non-conservative force. So this minus non-conservative force is going to increase as increase in velocity. In that case, your force is not going to be constant. You can't take out the integration, out of the integration. Okay. So what it says is the magnitude of the air resistance force is not constant, but depends upon the speed. Hence, it can be written as F dot ds seen during the work done by the variable force. Yeah, that's right. So it can be seen as a work done as a variable force. So your non-conservative forces will non-conservative force will eventually can create a variable force. The net force will be variable. That's what they want to say it. Okay. So and that's all about your conservative forces and the work energy theorem. In the next class, we will see about the principle of conservation of linear momentum. That also will be an interesting thing. Okay? Yeah.